So even though the title of this lesson is Mutations, we're really still going to keep talking about transcription and translation, but in a different context, in the context of things being changed. So the first thing we'll do is maybe just provide some definitions of what all of these words mean. When you hear the word mutation, I think a lot of people have this idea in their head that that means three-eyed fish, like that is what a mutation is. But all a mutation is a change to the sequence of DNA nucleotides. When you say it like that, it doesn't sound quite as horrible. And I want you to have in your head that not all mutations are going to make you or a fish have three eyes. Now mutations, so changes to the sequence of DNA nucleotides, can be spontaneous. Spontaneous means they just happen. Nothing drastic caused them. You weren't struck by lightning. You didn't fall in a vat of radioactive waste. They just happened. They happened because when DNA replication was occurring or during meiosis, a mistake got made. Something happened and the order of nucleotides changed just slightly. Sometimes, though, they can be induced by mutagens. So a mutagen is something that causes a mutation. And we could classify these mutagens into a couple of categories. They could be physical, for example, some sort of electromagnetic radiation. So if you have taken physics or are taking physics, or you remember learning about the electromagnetic spectrum previously, things like an X-ray or a gamma ray, any of those rays that exist, are something that could, not necessarily will, but could cause a change to the sequence of DNA nucleotides. If any of you have been to the dentist recently and you had your x-rays taken, they always put the big vest over you, and the person who's taking the x-ray will step out of the room because they don't want to be that close to the x-ray, because they're probably taking many x-rays a day and they don't want their body to be exposed to that because it could cause changes. If we're talking chemical, now here we're talking about some sort of substance, something that could potentially cause changes to your DNA. So there are lots of examples of things here. I don't want to just say toxic stuff in general, but if you think about a carcinogen, things that cause cancer, and I think if I ask you, do you know some things that could cause cancer? You might be able to list some things that could cause cancer, whether we're talking about like skin cancer, lung cancer, or other types of cancer. But those would be an example of something that's a chemical that could cause a change to your DNA. You don't have to know the details of one specific type of mutagen. I just want you to know that there are things, physical things, so things that aren't a substance, and chemical things, things that are a substance that could, not will, but could cause a change to the sequence of DNA nucleotides. Now, when we're thinking about mutations, we really have to remember what a somatic cell is and what a germinal cell is. Somatic cells go through mitosis, and if you think about them, they're not passed on. So if I think about my child, because I have one, if I were to get a DNA mutation in one of my somatic cells, say my skin cells, I would not have passed that on to her because it was in my somatic cells. Those aren't the cells that I'm passing on to the next generation. Germinal cells are the ones that eventually go through meiosis. Now you might recall they go through mitosis first and then meiosis, but they go through meiosis and they are passed on potentially. So it's important to note whether a mutation affects someone's somatic cells or their germinal cells, or potentially both. If you have a mutation in one of your germinal cells, that could be passed on to subsequent generations. Most of the mutations that happen are called point mutations. Point mutations means that one DNA nucleotide is affected. Now I say most because of course it's not everything, but all of the types we will talk about involve one nucleotide, one DNA nucleotide changing somehow that's going to cause the mutation. Now so far, does anyone want to ask any questions about any of these words? Yes, Kennedy. I didn't mean that like I purposely made it happen. I meant like if it happened. If one happened to me, if it occurred, yeah. No, I wouldn't go out searching for a mutation or trying to make one happen. Okay. So we're going to talk about some different categories of mutations. The first of which is a silent mutation. Now, much like its name suggests, silent mutations don't actually cause an overall change in the organism. I noticed a lot of you had some sort of grammar stuff going on in English. This is one of my pet peeves, effect versus affect. An effect with an E is a thing, it's a noun. Affect with an A is a verb. So there is no overall effect when a silent mutation happens. Now, how do we determine effect or not? It means no change in amino acid sequence. So when we're talking about no change in amino acid sequence, we're looking for something that will give us a change in DNA nucleotide, but not actually a change in the overall sequence. So if you put your data table away, maybe take it out again so that you can look and see what we're talking about here. So if you look at your data table, remember the other day we said the DNA code was redundant, that there were multiple codes that could give you the same amino acid. So I'm just going to pick one of the ones that has more than one code. Let's go at the top right of the table and look at the two codes, UGU and UGC, that both code for cysteine. So this is our mRNA. If I look at those two codons, they give me the same amino acid. In your daily review today, I said there were more than one correct way to answer the question, and that's because I told you the names of the amino acids, and for most of them, there was more than one mRNA codon that you could have picked that would have been correct. So I'm just looking, did you have one of the 2 or 4 or 6 correct codons that would have worked? Since the amino acid is cysteine in both cases, it wouldn't matter which of these two codons I had. That would mean that in the person's DNA, they would have the complement So I could say something like this. A mutation could occur where an adenine nucleotide is substituted by a guanine nucleotide, but the result is a silent mutation. Even though I've changed the DNA nucleotide, which changes the mRNA codon, I get the same amino acid. So it's possible that a question asks you what would happen if this nucleotide was replaced with another, and the answer might be nothing. Nothing will happen. You'll get the same protein because you'll get the same amino acid. Does anyone want to ask about that kind? Okay. Now the next kind of mutation is called a missense mutation. In a missense mutation, what happens is that, whoops, let's try this again. A nucleotide substitution causes a change in amino acid. And there are a couple of examples there, just so you can get an idea of the kind of thing that could happen. People always think, oh, mutation, bad, 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 don't want mutations. And sometimes, absolutely, mutations are bad, and bad things happen. For example, a one nucleotide substitution could cause a person to go from having normal red blood cells to sickle cell anemia. Does anyone know or remember what sickle cell anemia is? It's when your red blood cells kind of look like little half-moon shapes. They can't transport oxygen as effectively. So that's bad. Like, that is a bad thing that can happen because of a one nucleotide substitution. But there's other examples where a one nucleotide substitution will allow a person to produce an antibody that they weren't producing before, and that's actually good. Now, are these examples specifically super important? No. I just wanted to highlight that it could be negative or it could be positive. Most of the variation in the traits that we have is actually because of mutations. So the fact that there are different like hair and eye colors and things like that, which aren't, I don't think, bad traits, they're just traits, happened because of mutations. Mutations happened, and over many, many generations, different traits started showing. Now, in a missense mutation, we'll do the same thing. What's the person's DNA, mRNA, and what's the amino acid? We would need to have a change that caused us to produce a different amino acid. So, for example, if I started with A, C, A in my DNA, I would have U, G, U in my mRNA. And just like the last one, that would code for cysteine. Now, I could have a mutation that would give me something different in terms of my mRNA code. Let's say that instead of UGU as my mRNA code, I ended up with something like this. So the person, just like the last time, has a one nucleotide substitution in their DNA. So cytosine has replaced adenine. If we look at their mRNA, now I get UGG. UGG codes for tryptophan. That is not the same amino acid. So if a substitution happens like that and we get a different amino acid, it's called a missense mutation. Missense because now I'm not going to get the same sequence of amino acids that I had before. It could be bad, it could be good, it could be relatively neutral and just give you a different color of hair or color of eyes. So don't always assume that that means bad. Does anyone want to ask about the missense type? Now, there's another type of mutation called a nonsense mutation. In a nonsense mutation, usually what is happening is that a functional protein is not produced. But there are a couple of ways that this could happen. One of the ways is that the regulatory sequence could be affected. And by that, we mean the start or the stop codons. So if you remember on your data table, there's methionine, the one with 1 star. That's the initiator. Then there are 3 codons, UAA, UAG, UGA. They have 2 stars. They're all stop codons. Often what will happen in a nonsense mutation is that the start codon is removed or the stop codon is added where they weren't before. So we're messing with the regulatory sequence. So we'll do an example so that you can see how that might happen. So if we start with a DNA sequence like A, T, G, ATG would give in mRNA UAC, and UAC codes for tyrosine. Now, if we had a mutation that changed my DNA just slightly to A, T, T, so same thing that happened before, the G got changed to a T. My code becomes UAA, and that's a stop codon. So instead of producing an amino acid, I hit a stop. That means the ribosome is going to stop translation. If there were other amino acids after that one in the protein, they're not going to get added. Depending on where this happens in the chain, it could cause a huge, huge difference. If it's at the very end, it might not cause a big change, but if it's in the middle or close to the beginning, every amino acid that was supposed to come after it now is not going to be transcribed. So it could be a really big deal. Now the last one is called a frame shift mutation. In a frame shift mutation, we either insert or delete one nucleotide. When that happens, it causes every other nucleotide to shift. So we'll just make a DNA code. Now I made it a bit longer this time because to see the effect of a frame shift mutation, you really need to consider more than just the codon that you're looking at. If this was my DNA code, my mRNA code would be U, 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 A, G, 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 C, C. So my amino acid sequence, UUU codes for phenylalanine, AAA codes for lysine, GGG is glycine, and CCC is proline. So when we do this frame shift mutation, we are going to insert a nucleotide in the DNA code. We're just going to put one in. So I'm going to imagine, and then I'll rewrite it, that right here I insert an adenine. And so let's look at what the DNA code becomes. The first codon, still AAA, but now the second one is TAT. This T that's left over will be the beginning of the next codon, TCC, then CGG, and then a G all by itself. So look at how much we changed. Not only that nucleotide that we inserted, but now all of the codons are different than they were before. If we look at the mRNA that's going to give us, U, 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 A, U, A, G, 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 C, C. And then we look at the amino acid sequence that comes because of that. I still get phenylalanine for my UUU. AUA is isoleucine. AGG is arginine. And GCC, where's my GCC, is alanine. So I have the same first amino acid, but as soon as my insertion happened, all of the amino acids are different now because I've changed all of the codons. I could keep going in this chain, and very probably all of the amino acids will be different. So I'm still making amino acids, but is this protein going to be functional? It might be, but it's fairly unlikely that it will because it's not the code that was in the DNA. One of the things that's useful with mutations is that you can determine how close or how far someone's common ancestor is by looking at the number of mutations that have happened in their DNA compared to somebody else. So one of the things that scientists have started to study is mtDNA, which is mitochondrial DNA. And you might think, well, how is that different? One of the things researchers have discovered is that mitochondrial DNA is different than the DNA that is in the nucleus of your cell. So, why is it different? Well, one of the things that we think has occurred, I say think because it's a theory, is that when eukaryotic cells first came to be, they might have been the result of one prokaryotic cell engulfing another. It's called the endosymbiotic theory. If you remember Bio30E and the topic of evolution, I know I always briefly mention this one in my class. The endosymbiotic theory says that if we're talking about a eukaryotic cell that has a mitochondria in it, this is my really good drawing of that. So here's the cell, here's the mitochondrion. For that to happen, perhaps where it came from, based on its structure and the fact that the DNA is different, is that we had two prokaryotic cells and one engulfed the other. That's what we think. That there's lots of evidence that would support that this is where eukaryotic cells came from. So The reason mitochondrial DNA is different than the DNA in the nucleus is because it likely originated from a different cell. So, if we're thinking about your cells and your mitochondria, do you know which parent provides all the organelles that you have in your cells? Mom or dad? Mom. Mom provides all of the organelles. Now, why? Let's think about asymmetrical cytokinesis. Remember that during meiosis, instead of producing 4 gametes, the ogonium will produce an oocyte and a polar body, and then an oocyte and a polar body. We're only keeping one of them because the cytoplasm is not getting divided equally. The eventual egg that's being produced is getting basically all of the cytoplasm, whereas the polar bodies are not. It's asymmetrical. The mother then is contributing all the cytoplasm and organelles to the zygote. The father is contributing DNA. That is it. So, what does this mean? It means your mtDNA should be the same as your mother, as your siblings, or any maternal ancestor. So, if you compare your mitochondrial DNA and you have a brother or a sister, your mitochondrial DNA should be the same as theirs because you both got it from your mother and your mother contributed all of it. It's not a mix of DNA like the DNA in your nucleus. That came from both of your parents. Your mitochondria came only from your mother. So anyone who has the same maternal origin as you do should have the same mitochondrial DNA. So your mitochondrial DNA should match your mother's, which should match your grandmother's, which should match your great-grandmother's. If you were to follow mothers in a line, they should have the same mitochondrial DNA. Now, your father's mitochondrial DNA should match his mother's, but it won't match yours because fathers aren't passing on their mitochondrial DNA. So we can use the number of changes to mtDNA sequence to determine ancestry. So mutations happen. They happen spontaneously. And so if you compare your mitochondrial DNA to somebody else's, and it's close but not quite the same, we can count the number of changes and figure out kind of how far away your nearest common maternal relative is. If it's really similar to somebody else's mitochondrial DNA, you could assume that you're related to them. That would be a good assumption to make.